So now we call it as sampling distribution. We do not call it as probability distribution of x bar, we call it as a sampling distribution of a statistic. So x bar is a statistic and we are giving sampling distribution, we are identifying the sampling distribution of a statistic. So now one should ask a next question, what is the sampling distribution of sigma square? We will come to that, but at least the sampling distribution of x bar is very clean, neat, it is Gaussian and it makes only one simple assumption or two assumptions. Your sample size is greater than 30 and your underlying population is IID or at least independent. That is the clean assumption. N is greater than 30 is sufficient, because if you have looked at the normal table, what will happen? Your normal table, if you would have taken and then other table, so if n is less than 30, you can prove that it is a t distribution, we will come to that, and t and normal will merge after n greater than 30, okay. So we will talk about it, okay. So n greater than 30 is typically enough. So I will show you how things change. Sample mean for 200 simple random samples of size n equal to 5. So what did I do? I have taken 200 samples, 200 into 5, each sample is of size what? 5. So total number of data points used is 1000, okay, and these are mean of these 200 samples, each of size 5. Now I plot x bar. So this is what it is, right? So this is my 200 x bars, okay. So I plot them. How does it look? More or less getting to bell shape. I am just generating data, okay, I not did anything. Some n samples I have created 2000 samples, I have made it into buckets of 5, 200 x bars, plotted it. Now same thing, if I increase the data size to 20, okay, more and more Gaussian. So if I make it to 100, it would have actually become exact Gaussian. I think I have it, I do not know, yeah, n equals to 4, n equals to 10, 30, and if you increase it more and more, it will become perfect Gaussian. N equals to 4 only, it is clear, you are getting Gaussian, right. So this is the idea of, you know, this central limit theorem, and of course the more and more size you have, the better it is, it will converge to Gaussian better, that is all. Questions, concerns? This is our central limit theorem, clear? I have given some examples here. So the shape of the sampling distribution of x bar is, if x is normally distributed, then even better, x bar is 100% normally distributed. What I have did is, I have not made assumption, any assumption on x. If x is normal, then x bar is guaranteed normal, but even otherwise, if n is greater than 30, x bar is normal, provided it is IID. Okay. So sampling from a population that is not normal, I will show you. The following is table and gives the probability distribution for rolling a fair die. You are talking about rolling a die. What is the underlying distribution? Uniform distribution. All of them have same probabilities. You have the mean and variance, you know, 3.5, 1.708. Now this is my distribution of a fair die. Estimate the sampling distribution of x bar by obtaining 200 random samples of n equals to 4 and calculating the sample mean for each of the 200 samples. What am I saying? Now you throw a die, okay, 200, how many times? 200 into 4, 800 times, make it into buckets of 4, okay. So that way you will have 200 sample means, okay, and plot it, what do you get? You didn't get uniform. The original population is uniform, but distribution of x bar is, you see, that is what it is. I am just giving you. So what we are saying is, it is not, original distribution has not changed anything, it is still uniform, but the distribution of sample mean is Gaussian if n is greater than 30. Here we have taken 200 into 4, 800 samples, clean. Make sense? N equals to 10, it gets better, n equals to 30, close to a Gaussian. This is the histogram. See, many a times you may want to work with truncated Gaussian distribution. You will not work with Gaussian, you may want to work with truncated Gaussian. What is truncated? Where the truncation comes from picture? In real life, especially we will want to truncate it. You have to keep that in mind. It's typically a truncated distribution. Why? Your sensor cannot measure from minus infinity to infinity. No, right? So your sensor will have a range. So it could be Gaussian within the range, not typically minus infinity to infinity. And even if you look at the tables, minus infinity to a certain value, all of them accumulated, the CDF will be very, very small, because at the tails the values are very small, they are like outliers. Only at the center and 3 sigma it is important. Beyond 3 sigma, how much percentage is there? Only 0.3 percentage is there, 0.3 percentage, right? 99.7 percentage gets covered. 99.97 gets in. So 0.03 percentage, you can typically imagine, you are not leaving anything after 3 sigma. Okay, so that probability is typically small, the corners. Okay. Input. So there are two things when you deal with the system. One is input of interest, that is the input I give or input of interest, right? That typically will have relationships, right? And one input is what? Unknown, not controllable, and typically independent, like breathing rate, opening and closing, somebody coming in, right? These are some things not controllable. I can assume it to be a IID, and I assume additive noise and then say it is Gaussian. AC in this room, I control it. Now if I say AC is also independent, that is not true. I am controlling it, there is a pattern to it. So input itself, you have to demark it into two parts. One is which is controllable and which has a pattern, because I give it. One is uncontrollable, and typically there is less and less pattern, and most often there is no pattern. That is what I assume it to be IID. The input is what? If we keep AC as constant and remove this, all other things are independent. Noise is independent, right? The fluctuation is because of what? Some independency. The input is only considered to be model, independent. Okay. Okay, I understand where you are coming from. Okay. Okay, so this input for this temperature case, what do I assume? IID white. But there is a random process which takes this input and then gives out a temperature which can be related, which depends on the pass. So it is a random process. So when you talk about an input and output, there is a system which is sitting here. As a body is a system which takes in all these random inputs, like my thinking, the external weather, everything, and then produces an EEG as an output from the brain, electrical output, which has relationship. So this system relationship is seen in the output. It is not the input relation, right? Input is processed by the system. So system relation. So what are you modeling? Are you modeling the signal or are you modeling the system? You never model a signal, right? You don't model a signal, although you say modeling EEG, you are actually not modeling EEG. That is not technically correct. You are modeling the system that generated this EEG. We call it as time series, but also on the time series was also we are always talking about the system. What do we model? We model a system, not a signal. We only do signal processing to model the system that generated this. You want to model the normal behavior of brain using EEG or abnormalities. So after modeling the EEG, what are you going to talk about? Are you going to talk about EEG is faulty, or are you talking about the EEG generated brain has some issue? So you are always interested in the system. Okay, so there are the subtleties. Clear? So this is about the mean of the distribution is equal to the mean of the parent population. The mean of the sampling distribution is equal to the mean of the shape. Okay, this is normal. The shape of the distribution of the sample becomes approximately normal as sample size n increases regardless of the shape of the population. This is very, very important. Okay, so this is the key point in central limit theorem. This need not be, the underlying distribution need not be even continuous. It can also be discrete, and still we can show that sample mean follows Gaussian. So suppose that a random sample of size n is obtained from a population in which either does or does not have a certain characteristic, like an anomaly or not anomaly, like diabetic or not diabetic. What is the proportion now? Proportion is x by n, right? We are talking about the proportion of the people having a issue or not having an issue. This is discrete, right? Probability proportions x by n, where x is the number of individuals in the sample with specified characteristic. The sample proportion now, instead of what is the statistic here, the statistic is not x bar. What is the statistic here? Proportion is the statistic. You always do not think mean and variance. Mean and variance are not good for what? When I take a discrete distribution, or when I take a discrete random variable, or let us say let us take a classification problem. I want to classify between dog and a cat. Is mean a good number? Mean is not always good. Mean is good for continuous values. For a classification problem, what do you want to have? You want less number of errors, right? Or you want more number of correct classification. When you talk about more number, what is it? What is the statistic? What is it? Mode. You have read mean, median, mode. Mode, when does it become useful? Discrete, categorical variables. Discrete variables, mode becomes useful. Mode are proportions. Proportion is nothing but mode only. In a sense, I am dividing it by n, right? In a sense, it is for categorical variables. Okay, you don't use mean or median, you use mode. What is the median value for classification problem? Like 1000 images I have, 700 are cat, 300 are dog. What is the median value mean here? Nothing. But if I say mode is this one, the most occurring is correctly classified, then it makes sense. You all have heard of k means clustering? K means clustering. Have you heard of k mode clustering? Okay, that tells you. For a continuous variable, you use mean. For a discrete case, categorical variable, you use mode. Okay. So I talked about mean and median, did not talk about mode, because we will come to a point where that will happen. So here it is a categorical variable, so we say the statistic is proportion. And what are we interested in? We are interested in estimating the population proportion from a sample proportion, and we can show here again that this is my p hat, okay, for a certain problem. 349 responded yes, okay, out of 1745. So p hat is 0.2. Okay. Now if I start collecting for n equals to 10 samples, 50, 100, each bucket is 10, 50, 100, and then repeat the exercise. 300 sample proportions of size 10, size 50, size 100. You see a clean normal distribution coming out. What is the underlying distribution? Underlying, I am talking about discrete categorical case. What is the output of the statistic? Gaussian. Right? So that is where things are. Even X bar, R proportions, etc. As long as the sample is independent, that is the underlying population is independent, Gaussianity is the best outcome. So in fact, sum of n Gaussian random variables follows sum of n independent random variables follows Gaussian distribution. So key points: as the sample size n increases, the shape of the sample distribution of the sample proportion becomes normal. The mean of the sample distribution of the sample proportion equals that of the population distribution. Expectation of p hat equals to p. The standard deviation of the sampling distribution of the sample proportion decreases as n increases, because we know variance of x bar equals to sigma squared by n. As n increases, variance of x bar, that is what you saw here. See the width decreases, spread decreases. Clear? And now for p hat, I can review what is this sampling distribution of p hat. Can anyone tell how I would have arrived at this? Can anyone tell me how did I arrive at this number? What is the underlying distribution here? Correct or wrong? Two outcomes. What is the underlying distribution? Bernoulli trial or binomial sequence? It's a sequence, right, for more participants. So sequence of Bernoulli trials is what? Binomial distribution. What is the variance of binomial distribution? NPQ. So this is nothing but variance of p hat equals to NPQ. What is PQ? And we know why variance of p hat should be what? Sigma squared by n, right? So this is nothing but this is variance of p hat is sigma squared by, this should be, I think NPQ should be somewhere. Am I missing something? P hat sigma squared by n. Okay, if I take a square root square p into 1 minus p by n squared. Okay, so this is sigma squared by n, right? So this is NPQ. Okay, I will have to derive it. I don't know whether I am making any mistake. So this should be from this part, and then variance of p hat. So this should be somewhere n squared should come. That is where the challenge is. I will have to check. Okay, but this is simply from the binomial distribution idea, variance of p hat. Okay. So NP into 1 minus p is what they are also we have said. So in this case, even greater than 10 it works. Okay, so not even 30. So we have said mu p. So far we have said two quantities. We first learnt about mu and then related as x bar. The sample quantity is x bar. Okay, and then this is p hat. Okay, and then this distribution is distribution of x, sampling distribution is, both sampling distribution is normal. Okay, so far we have learned two target parameters mu and p, and then the sample statistic is x bar and p hat. Both of them follow normal distribution when n is greater than 30, and then expectation of x bar equals to mu and variance of x bar equals to sigma squared by n. Okay, and then expectation of p hat equals to p and variance of p hat equals to square root of p into 1 minus p divided by n. Okay. These are the two targets, corresponding sampling distributions, and then the values.